record. Okay, so our focus of the problem is that we're trying to create an arrangement of parts on a Turing Tumble simulator machine so that the truth table displayed in table 3 right here matches that of the arrangement statement that we created. The statement being negation P and Q or R and true, which acts as the DNF form of W, which is this truth table here. This indicates that no matter what the value of negation P and Q is, at the end of the day, the value of R will always be true. So how do we show it? Well, first we need to note down to ourselves that the Turing-Tumble expression, expressed in this diagram right here, if P then Q, is logically equivalent to this part of the statement, negation P and Q. Now, based on the example given right here, it should also be noted that the expression being described is negation P or Q. Now, it may raise some questions and eyebrows on how the OR operator is indicated. Well, it's explained further with the inclusion of these green ramps. With the left side being dominant with green ramps, it indicates that we're utilizing the OR operator. So if we were to reflect it, this entire diagram right here, as a mirror image, we would have this image right here, which would indicate negation P and Q. Now I'm going to test it out by performing 4 inputs. Input 1, which falls into the false intersector. Oh, sorry. Accidentally changed the colors. Second ball fell into the true intersector. Third ball falls into the false intersector again. And the fourth input falls into the false intersector. So we've displayed negation P and Q. But what we really want to display and check is if this expression here, negation P and Q or R and true, is a match with this truth table, which means we're going to have to rearrange the simulator to include another bit representing R. Luckily for myself, I've already created it. Now, since we're utilizing the OR operator, this means that we'll have to I had to rearrange the green ramps, so that way it indicates that we're telling the Turing Tumble, hey, you know what? I want to utilize an OR operator, so here's the diagram indicating that I'm utilizing an OR operator. Now that we set up the entire thing, having the P, Q, and R bits representing true at the beginning, we're going to test out the simulator by performing 8 inputs. Keep in mind, we're trying to see if this simulation is a match with table 3's truth values. So to do that, we need to compare each of the truth values from this example table with the bits that are shown on the diagram here during each input. So let's start this off. Input number 1, false, true, false. Now, head over to the table, look for false, true, false. It falls into the 6th row. Next input, true, false, false. Look for the row, 4th row. Input 3, false, false, true. Look at the table again, false, false, true. 4th input, true, true, false. Head on back to the table. 2nd row, 5th input, false, true, true. This falls into the 5th row. 6th input, true, false, true. Falls into the 3rd row. 7th input, false, false, false. Falls into the 8th input. or sorry, the 8th row, and the 8th and final input will be true, 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 leading all the way back to the 3rd row. And there you have it. Based on the inputs that we created through this turing tumble arrangement, we've confirmed that there is a match with the truth values of table 3. And there you have it.